Maybe I take off the mask. All right. Yeah, so great. So thank you very much. And yeah, we were talking about the batteries, and I showed you a little bit about the internal design, but there are also different designs of cells: cylindrical cells, pouch-packed cells, prismatic cells, as you can see here. They all have somehow different properties, and different car manufacturers use different sizes, designs. Tesla, for example, always used a small cylindrical cell. Now they have designed a larger cell, which might become something like a standard in the automotive industry. We will see. This is how this looks from the inside. So you have these electrodes, thickness 20 to 100 micrometers, wounded up to put them in the cylindrical cell. So you put sheets on top of each other. These are all well-established processes these days. This is for more details, such a cylindrical cell. This is a computer tomographic picture. With the computer tomographs today, we can really have a look into these batteries to see also what may change during aging in such batteries. And yeah, if we look into this, when we want to learn really how battery has aged, then we have to open the battery cells. These are the electrodes which are inside the battery, the copper and the aluminum current collectors, and then the active materials on top of them. And this is what we're doing in our research. So we're looking really into these batteries to understand very precisely what happens during the operation in the lab, in the field, to improve then operating strategies and also designs. Some cell manufacturers have a totally new shape battery. This is a so-called blade battery cell. This was launched by Chinese companies, 90 centimeters in length. There's also from CATL a battery 1.40 meters in length, and they come then in the ground of the car and like lamellas, more or less. So it becomes really integrated part of the car in total. Now, at this point in time, the car manufacturers, at least from the upper cars, go to higher cell voltages, battery pack voltages up to 800 volt. This is necessary for the very high charging powers. I mentioned earlier that the charging power goes towards 350 kilowatt for the upper class cars. At 800 volt, this is still something more than 500, something in the range of 500 amps. Yeah? So this requires huge sockets and plugs and cables and so on. But, and this is important, from the battery's point of view, higher voltage is always, the higher the voltage is, the more cells you have to put in series. And as the worst cell in such a series connection always limits lifetime and performance, the overall performance and the reliability of the systems decreases with increasing voltage. Other things improve: cable diameters, plugs, fuses, connectors, and so on. But the battery itself is suffering from the higher voltages. And I would like to show you a few slides which were published 2 years ago by Tesla, which show quite well the strategy in the automotive industry or at the battery manufacturers to bring the technology forward. Tesla is, to a certain extent, with regard to battery technology, quite conservative. So they are not claiming that things like solid-state batteries may come or totally new batteries. They are working really on a step-by-step improvement of today's technology, but they achieve their targets. So different from those who always try to claim that they can found something totally new. And in their plan, they have shown how they hope to reduce the cost of the batteries by a factor of 2, roughly, within 5 to 6 years. They talked about cell design, cell manufacturing, anode and cathode materials, and vehicle integration. And one of the things in cell design is that they changed the batteries to so-called tabless batteries, where the current is not extracted at a certain point in the winding, but overall, which gives a much more homogeneous temperature distribution, also allows for a better heat transfer to the outside, and gives a lower internal resistance. And it is always interesting to see that the things which have been proposed here are taken up by others now more and more. Another thing where they say we have significant improvements potential is in the production process of the electrodes. The active materials are typically today pasted on the current collectors as a wet paste. Yeah? And then it requires afterwards, first of all, drying of this. The solvent must be recovered and so on. And what Tesla would like to go for is a so-called dry coating process. And they have already acquired years ago a company working on this. And they say if we achieve this, we can reduce, we can reduce the footprint of our production site for this step of coating and for drying by a factor of 10. And also the energy usage is reduced by a factor of 10 for this specific production process. So they want to go with powder in this dry coating process. Still has challenges, but it's for sure the right way to go to get these reductions in footprints and in energy productivity for this specific process. The other thing they are claiming is to integrate the batteries more into the cars. Today, typically, first of all, you build modules, and these sub-modules, several of them are then put into a battery pack and then into the car. And this future process then means cell to pack, rather than cell to module and module to pack, going from cell directly into the pack and integrating this into the car, into the structure, which saves weight and one level of complexity. So this is also something which reduces cost. So what they say is by the new cell design they are going for, they may save 14%, in the production process 18%, in the graphite 5% by using silicon, in the anode material by reducing cobalt content, and by integration into the car. And all of these things on their own are quite realistic. We're not absolutely sure about the silicon and the carbon, and the dry coating has still been shown that it works also for the lithium-ion batteries, but it was established, for example, for supercapacitors. So it's not an unknown technology. And generally, I have to say I like this, that people come and say, we are doing very good engineering, and then we do here an improvement of 5 to 10% and there and there and there, but not promising some miracles. This is what the conventional car manufacturers often say. They say, we know we don't get too much in today's technologies because they're the next generation of batteries, solid state or metal air, and then we are going into this because everything is new and so on. But the point is, this doesn't happen in the coming 10 years, so it is necessary to go into the existing technology. And with another cost reduction then of more than 50%, the price would be in the range of 50 euros on a cell level for per kilowatt hour. In the last year, the prices somehow increased due to increasing raw material prices, but I come back to this in a minute. And with this, they said, beside the normal economy of scale trajectory, due to these new technologies, they can get significantly faster down in the cost. And in Germany, just they built a new battery gigafactory, which should be based on these principles. So then I would like to say a little bit about safety, because this is for sure also which is discussed a lot about electric vehicles. We all know probably pictures like this from burning cars and some callbacks and so on. So these things happen, that's not a question. Yeah? And we also can analyze meanwhile, because the number of cars is not that small anymore, the statistics, and then first of all, we find out that the majority of these problems comes from accidents. Yeah? So this is not coming from the technology on its own. Maybe only something like 1/3 of the fires somehow are caused by defects of the batteries themselves. The rest is more or less caused from the outside. We also can have a look where the recalls in the automotive industry have been with regards to batteries, and they are more with regard to some problems in the production process and the quality, but they typically do not result, or these callbacks are early enough to avoid any major problems. Two things, nevertheless, have to be looked at. First of all, a fire in the battery always goes via a thermal process. So when we look on the time scale here, we see that temperatures of the batteries, first of all, increase, and only after a while, this might result in a fire. That's very important for safety reasons. For example, the Chinese government has a law that says it must be assured that the battery management system tells the driver at least 5 minutes ahead that a fire could come up. Yeah? So saying something like, don't panic, yeah? Drive your car to the side, park it, leave the car, and then wait. Yeah? This is a challenge, but it is possible because we typically have these processes. Yeah? So with a good thermal monitoring and so on, this can be achieved. Nevertheless, if this happens for sure, then we are in trouble. Once this happens, fire extinguishing is not such a miracle as it's sometimes discussed. Use water. Yeah? The most important is to cool the battery, and this is best done by water. Some people think you should not extinguish battery fire with water because there are metals which may burn, and metal fire is even accelerated by water. But it's not water that burns. It's all typically organic materials, organic electrolytes, separators, graphite, and whatever. This is what really burns, so water is a good thing. And if you have a problem with a battery, and the battery is in a state where it is not really clear what the situation is, then the best thing is to put it into the car into a container to separate it in case something will happen. So all these things are absolutely necessary, but the important thing is the number of fires which we really have in electric vehicles is dramatically lower than in conventional cars. Yeah? So we know from the statistics, here these are numbers for the United States. These are the number of vehicles on fire per billion miles driven. Yeah? So not in absolute numbers, normalized to the mileage of the cars. And here you can see that the number of conventional cars which goes on fire is a factor of 10 higher than battery electric vehicles. Nevertheless, because the reports in the media always show if an electric vehicle burns, most people have in mind electric vehicles have a significantly higher risk. The other thing, it's the other way around. Yeah? So this is quite important to know. There are in the United States something like 200,000 cars per year on fire. And in Germany it's 40,000. Same number per car, just the United States have more cars and therefore they have a higher number of fires. But this is normal day-to-day business and nobody cares. The same as so many people die in traffic, in traffic on roads or get injured, this is accepted. So this is one of the big problems we have in introducing new technologies because they are not always measured with the same in the same way as the existing technologies. And we can see this in many different fields. And this is anyway also quite interesting because there's one technology which is always discussed as a more safe technology, and these are the so-called solid-state batteries. Yeah? But this also gives you a picture how difficult it is to get into a market with an argument of being more safe. Yeah? Because if you have already gained 90%, yeah, then more safe means somewhat more safe based on this. So just from a commercial point of view, if you look for an insurance, 90% of the gain is already done by switching to today's batteries. And then there's just a very small additional number of fires which might be prevented by a more safe technology. So the value from an insurance perspective is not very high. So and then there are some other often heard statements and what lies behind. I think I won't go to this. You may read this, and if you have questions on this, we can discuss it in the break, because there are some of these things which are very often mentioned with regard to batteries, low temperatures, fire extinguishing, operation range, storing a battery at full state of charge, and so on. And it is always worth to really look to what is behind. Yeah? So in many cases, this is different from what the typical rumors are. But what we really have, what we really have a very real problem is, at the moment, supply of raw materials. If we look to the demand on raw materials, and for sure it always depends on the special chemistry. I did this analysis for a so-called 811 material. This means it has in the cathode 8 shares of nickel, 1 share of manganese, 1 share of cobalt. So this is a modern material composition. And then if you look to a 100 kilowatt hour battery, you can calculate how much nickel, manganese, cobalt, lithium, aluminium, and copper. So this is only listing the metals are needed. And for such a 100 kilowatt hour battery in an upper class car, you need about 85 kilograms of nickel, close to 10 kilograms manganese, 11 kilograms of cobalt, 9 kilograms of lithium, 38 kilograms of aluminium, and 74 kilograms of copper. These are significant numbers. They are real significant numbers. And if we then go to these maybe 1,000 gigawatt hours of capacity we will need 2025 or maybe 2026, we can simply calculate how many metric tons of materials are needed. But these numbers are still not really telling you a lot. It becomes more interesting if you compare this with the actual production of these materials from the mines. Yeah? And this is what you can see here in the last 2 columns. This is what 2017 was produced from the primary mines, according to the United States Geological Survey. This is probably the best databases you can have when you look to raw materials, and then you can look what this means. Yeah? So, and it means simply for the 1,000 gigawatt hour battery production, we would need 41% more nickel compared with what was produced in 2017. We need just 1% more manganese. We need 100% more, so doubling of the production of cobalt. We need 14% more lithium, so tripling the production of lithium. Aluminium and copper, again, are small. Yeah? And this is a major challenge. It's not the problem that we do not have sufficient raw materials. There are sufficient raw materials in the world for all the cars and whatever is needed. Yeah? So these are just these numbers here. Here you can see, for example, the forecast the reported worldwide reserves and resources on lithium, again, according to the United States Geological Survey. And you can see starting in 2009, quite suddenly, these numbers increased more and more. Yeah? And this is exactly what we know, for example, from the oil resources. Yeah? In 1970, people said it's 40 years, and then all the oil resources would be used up. Now it's 50 years later, and there's at least still for another 40 to 50 years oil. Yeah? because people looked more in detail. They have new technologies. So technology in the oil industry improved dramatically. And if the price rises, you anyway can get also to more expensive mining processes. And the same is true for lithium. Everybody is now looking for lithium, and even in Germany, we have lithium resources. I'm not sure that they ever will be used because the price will be relatively high because the concentration is low, but it is there. So we do not have a problem with resources, but with the mining capacities. And building up new mining capacities takes easily 5 years, 6 years, 7 years. This is a real challenge. Same problem in the oil and gas industry. If the oil price is very high, it's not that easy to say, okay, then we just increase the mining capacities for the oil and the gas. It really takes time, long-term investments, and the investors have to be sure that a relatively high price maintains over a long while. But this, nevertheless, due to this dramatic change in mind in the automotive industry, now to go very hard into the electromobility, these curves, these growth curves are so exponential that it will be difficult in the coming few years to really follow the demand with increased mining capacities. And this is something we can see in part in prices. These are numbers from metal exchanges, different metal exchanges in the world, because, for example, lithium carbonate, the main product for the chemical industry, is traded mainly in China. Others are traded mainly in London Metal Exchange. And it's not so much about these numbers here itself, because some return to tons and some to pound, whatever, it doesn't matter. But the curves are of interest. And you can see the lithium price is, this is the biggest problem for a long while, was really low. And then the price increased by a factor of 10, and it maintained, meanwhile, 1.5 years or something like this on a very high level. So lithium resources generally are quite well distributed all over the world, but for some reason China managed to get almost a monopoly on the first production process. So from the lithium coming from the mines, for example, also from Australia, the things are shipped to China, and they then produce a lot lithium carbonate as a precursor then for the further chemical productions. In cobalt, we had 2 peaks here in the prices, but the prices already is going down again. Probably also because meanwhile, probably everybody has understood that the cobalt content in the batteries can be decreased dramatically. So the first lithium-ion batteries on the market in 1991, they had per kilowatt hour, let me say, if we call this 100% cobalt, then a modern lithium-ion battery from Tesla has, compared with this, only 5% of cobalt per kilowatt hour anymore. So the cobalt content was already dramatically reduced. So a shortage in cobalt will probably not the problem. Therefore, on the other hand, the demand in nickel has increased dramatically. This peak was due to a trading problem mainly, and but nevertheless the price shows is going somewhat upward. Manganese, aluminium, and copper are not the things we are really looking too much into. This is not the main problem. And then if you look into the demands here for the 100 kilowatt, for the 100 kilowatt hour battery, and you multiply this with the prices from the metal exchange, for sure, in this case, it's the end of 2021, the prices here, then you can have a look what is a share. So roughly 1/3 is going to the nickel, more than 1/3 to the lithium at the moment, and 15% to the cobalt. This adds up to something like 46 euros per kilowatt hour. This also shows us it is possible to bring down the price further because the metal the metal materials have prices which allow further decrease in price. Lithium, as I said, is the main problem. This is a reason why sodium-based batteries gained a lot of lots of activities have been put on sodium-based batteries. But as I said, the users in vehicles will rather feel if they are driven by a lithium iron phosphate battery, for example, or a sodium ion-based battery. This will more or less, from the user's perspective, it will be the same. But we get rid of the problems with nickel and cobalt. And this is really an interesting thing. We will see CATL has announced already for 2022 major market introduction. This was not so major as I have announced it, but nevertheless, the first products are available on the market, and maybe it takes another year or something like this, but it can go relatively fast because, as I said, they can go on the same production lines, and many things are very similar compared with, for example, the lithium iron phosphate. But nevertheless, this for sure have to be looked at, but it is also important to understand this high prices for the lithium at the moment, or any shortages, are not really a reason to say I'm going away from the batteries and maybe going to the fuel cells, because this is just a matter of very few years. The capacities are there, so the reserves are there. And we know that there are several countries are on the way to invest into more mining capacities, so this problem will be solved faster than you can introduce any other technology. And with this in context, it is also worth looking into recycling. Especially the European Union puts a lot of emphasis on recycling. European Union tries to get more independence from raw material imports, and this comes along with a very detailed recycling strategy. However, even though they have defined very precisely how many batteries must be recycled and also what the share of recycled materials must be in new batteries and so on, it simply takes time. So you can see here once again in blue this ramp-up curve, estimated ramp-up curve of the sales of electric vehicles. And now if we assume that the lifetime of the cars, of the batteries in the cars, will be 10 years before they go into recycling, then you can see that the amount of material which comes from recycled batteries, this is here the yellow curve. So even in 2035, you might be able to serve 25% of the battery material from recycling. The other batteries are still simply in operation. So until we get really to a 100% recycling quota, it's getting 2045 or something like this. Always assumed that the technology will be still the same and so on. So very simplified calculations, but it shows what many people say, oh, problem with raw materials, so we do recycling. No, not possible. So we need, for a long while, we need the primary mines. So we need this. And this is also which is really important in the discussions. So many people fighting for a new world and a better world and clean world and so on, they think, and then we can reduce mining activities and so on. And yes, mining is a dirty business. That's not a question. And it is in coal next to my house, 15 kilometers from me away and so on. But we need it. We just can try to reduce the demand, but we won't get into a new world as long as we want to have a standard of living as today, with an air conditioning system working and whatever. Then we will also need raw materials in the future. Maybe other than today in part, but we will need it. It's no question. So these are some of these proposals on recycling. I don't want to go through these numbers. You can read them if you want to. So Just as an example, the European Union has said from 2026 onwards, 90% of cobalt, nickel, and copper must be recycled from those batteries which go into the recycling process. By the way, the largest amount of batteries going to recycling these days are the scratch from the production lines. There's always a certain scratch of batteries which do not fulfill the quality standards, and this is what is mainly going to the recycling processes these days. And so having said that, we can have a look what are technology trends. First of all, for the automotive industry point of view, there is the main trend is towards lower cost. Yeah? It's not anymore towards higher energy densities. Yeah? And this we can see very clearly on the so-called lithium iron phosphate technology, not new. Yeah? So 15 years ago, more already important technology. The lithium iron phosphate batteries allow energy density somewhere in the range of maybe 160 to 180 watt-hours per kilogram, whereas the nickel, manganese, cobalt-based materials can go in the range of 270, 280, 290 watt-hours already today, and 300 watt-hours per kilogram will be achieved. But in the modern cars, as I have shown to you, in the surfboard below, in the ground floor of the chassis, there is sufficient space. And as the electric machines are so powerful, the users of a car will not feel if there are 200 kilograms more or less of weight in the car. Relevance is the cost. And if we have cars which are not made for 500 or more kilometers of driving range, then there is even sufficient space in there to go with a relatively or with a significantly lower energy density battery as LFP. And this is exactly the reason why sodium-based batteries suddenly have a chance, because their energy density will also not be significantly above the lithium iron phosphate, so they will not play a game in the master class of batteries, but from the cost point of view, they have the potential to be significantly cheaper. Yeah? But this is important to have in mind. Yeah? So higher energy densities are very often named as most important target in research and so on. This is not right. Yeah? And this is very similar, for example, to photovoltaics. Yeah? For the world record efficiency in silicon photovoltaics over 10, 15 years more or less stagnated. There were no new world records. All the researchers put their emphasis on reducing the cost. So keeping more or less the achieved efficiency, but trying to achieve this with lower cost silicon, means more impurities, with less production processes and so on. So to drive down the specific cost. Because the sun is for free anyway, so at the end of the day, the only what counts is what does the kilowatt hour cost, which comes out of this. Low efficiencies are not good as well, no question, because you have more land use and cables and whatever, but at a certain point of time, or at a certain level, it's all about efficiency in this case, and here it's all about cost. So sodium-ion-based batteries, therefore, are interesting, especially because they are not only using no lithium, but also no cobalt here. This is why this is an interesting technology. Once again, because you can put them also on the same production lines. Because if you would have to set up all the production lines, then you have this drawback, not having the economy of scale effects, and this would make it more difficult to bring this into the market. Yeah, and then there are more foreseeable technologies or alternative materials. Some of them, like the lithium-sulfur batteries, this is a technology which is still followed up, especially here for very high energy densities, which might be of interest in aviation. In aviation, energy density is everything. No question. So, yeah, but yeah, I don't want to look into these details too much, but there are lots of things ongoing. Most of them are incremental, so it's a continuous process. We do not expect in the coming 10 years any totally game-changing technology. Yeah? The game changers are prices. So same as in renewable energies. The technology for wind turbines and PV haven't changed in the last 20 years significantly, but what has changed is price, by orders of 10, 20 or more. And this is a game changer. So it's not the improvement in the technology itself. So I plan to say a little bit about charging infrastructure, but I think I will skip this because I would like to switch over directly to hydrogen now. So when talking about hydrogen, then also, first of all, it's important to get aware maybe about some of the major properties of hydrogen. Yeah, there are also a lot of rumors and thinking about hydrogen in the minds of the people. First of all, hydrogen, element number 1 in the periodic system, the smallest molecule we have, the best friend of all physicists because it's such an easy atom, 1 proton, 1 electron, very easy. Nothing can be described better in models as hydrogen. But this is only a side remark. One of the questions is especially also is how we can store it. Yeah? And there, unfortunately, hydrogen has a very uncomfortable anomaly because other than most of the other gases, you cannot liquefy it by compressing. More or less all gases can be liquefied if you simply compress them more and more and more and more. But this is not the case with hydrogen. You can compress whatever you want, it will not liquefy. And this means you have to cool it down. And unfortunately, the boiling temperature is low. Yeah? It is somewhere in the range of the melting point, somewhere here, minus 259 degrees centigrade. So this is in the, what is it, 15 Kelvin or something like this. So very, very cold. Yeah? So if you want to have liquefied hydrogen, you have to cool it down. And today's processes need about 1/3 of the energy which is stored in the hydrogen for this liquefaction process. So 1/3 of the energy is gone when you liquefy this. And generally, hydrogen is quite reactive. So this is also the reason why it burns so nicely. This is for sure the thing we would like to have. Another thing which needs to be looked at, as the molecule is so small, it is relatively easy, diffuses also through many different materials. So you need very special steel, for example, if you want to build a hydrogen storage system, because otherwise the hydrogen may diffuse into the steel structure and this will destroy the structure over time. And then people have things about hydrogen like this in mind. Yeah? So I don't know, but I don't know if you know this, but the left-hand picture is something what probably every German has in mind when talking about hydrogen. Yeah? So this was a Zeppelin, yeah? Which just traveled over the Atlantic Ocean, and in New York it was hit by a spark. Yeah? And it went into fire. Yeah? So this was more or less the end of the era of these Zeppelins here, which were really interesting airships at these times. Today, in these cases, you typically use helium, yeah, for this, which is much more expensive, but which is not flammable. Yeah? But nevertheless, the big question is there an increased problem with the safety of hydrogen? And this is a question which, again, couldn't be answered something like with yes or no. For example, here on the left-hand side, you see a property of hydrogen. Here on the right-hand side, this is a conventional gas vehicle which gets into fire, and this is a hydrogen tank which gets into fire. Yeah? And what you can see is due to the light molecule, hydrogen really has a flame which goes straight upwards, whereas if you have natural gas, the rupture goes to all sides. So therefore, the collateral damages of a conventional gas fire are higher than from hydrogen. And if you look to some safety properties of hydrogen, we can see that the ignition temperature is a little bit higher in hydrogen, which means a little more safety. The flame temperatures are relatively similar. The flammability in ambient, so hydrogen can burn or can go into ignition in ambient air if the concentration is between 4 and 75%, whereas methane only can burn if the concentration is somewhere between 5 and 15% roughly. What is the most important difference maybe is if we look here to the necessary ignition energy. This is at 30% hydrogen concentration, significantly smaller than methane. This means if you have a critical concentration of methane or hydrogen, then it's much more likely that the hydrogen will ignite. Because you need significantly less energy, and maybe already the switching of the light switch is sufficient to bring it to ignite the explosion. However, on the other hand, as hydrogen is such light material, its diffusion is also extremely fast. So if you have a leakage in a hydrogen pipe or in a methane pipe, then the risk that a critical concentration appears is significantly less with hydrogen, because the hydrogen diffuses so fast away, whereas the methane concentrates. So this is why I say you cannot say the one is more safe than the other one. So if you have the critical concentration, hydrogen is more, they have a higher danger for an explosion with hydrogen. But to get into the critical concentration is more likely for the methane. So the message is, if handled professionally and well, from my point of view, we must not fear that hydrogen to any extent is more dangerous than natural gas, for example. It has to be handled with care, no question. Same is true for the batteries. So you need high quality in everything. You need professional handling, professional products. But if this is done, then there is no need for fear from hydrogen that it might be significantly more dangerous. All right, so the next thing about hydrogen, here I would like to show you some results from a project we just have done or better to say other way around. We have in Germany since 8 to 9 years, we have a counseling project of our national science academies. So Leopoldina, the AKATech, the German Academy of Technology Science, and the union of all the others, all the other German science academies, they have a joint project on all the interdisciplinary questions on the Energiewende, so the change of the energy system, to counsel our national government, our state governments, the ministries, and to a certain extent also the society. And I have the privilege to lead this project since 5 to 6 years now, 5 years? Yeah, 5 to 6 years now. And one of the projects, what we have done there is a very comprehensive analysis of the cost of hydrogen imports. I mentioned earlier, Europe most probably needs import of energy carriers. And the question is, first of all, beside the question if we have sufficient hydrogen, how can we bring hydrogen from somewhere in the world to Europe? Or to Germany, this doesn't matter, that's the same in this case. And from this I would like to show you some results, adding some other information. So what we have looked for is, first of all, what is the final product we really need? Is it hydrogen liquid in gas, or it is already in compounds? So is it part of ammonia? Ammonia is also produced from hydrogen, or LOHC. This is liquid organic hydrogen carriers, or synthetic fuels like ammonia, methane, methanol. Fischer-Tropsch products is the conventional hydrocarbons, the liquid hydrocarbons. So the question is, how would you like, or what do you really need? Yeah? So for the chemical industry, for example, which I mentioned earlier, we need mainly these oil equivalent products, so we don't need the hydrogen on its own. If you want to produce ammonia, which is the main product for the production of fertilizers, yeah, then you need directly hydrogen. But the question is, should we import then hydrogen and produce ammonia in Europe or wherever, or should we better directly import the ammonia? Yeah? So these are things which have to be looked at, and then we looked at for transport in pipelines and in ships, and for all these different combinations. Yeah? So we have here either pipelines or ships, and here we have the different products, and we analyze for all of them, depending on distances and certain assumptions, what are the costs for simply these type of processes. And before we're going into this, it is worth to look into some of the technologies which are needed there. And this is, first of all, hydrogen transport in pipelines. Yeah, so generally, this is possible. There are materials from which you can build pipelines, even with this problem of diffusion of hydrogen into metals and whatever. And this is an established technology. In Germany, for example, we have since 40 or 50 years, we have hydrogen pipelines. Because we have very strong chemical industry, and in some parts of the chemical industry, as a side product, hydrogen was produced all times, yeah? And this was then transported via pipelines to other chemical sites, chemical production sites for usage. So this is an established technology, safety regulations are there, and so on, so it can be done. But it is also worth mentioning that if you transport hydrogen as a gas, the energy you transport is per volume of gas only 1/3 compared with methane. Yeah, so if you transport natural gas, methane, in the same pipeline, if you use the same pressure, you have 3 times more energy. This is, chemically speaking, very, very simple, because the energy in chemistry is always in the electron bindings. Hydrogen has one electron here, 1 electron there, and this is more or less the energy where the energy is stored. And in methane, you have 1 carbon, and then you have 4 hydrogens here around. So 4 times you have here energy stored. Yeah? Simply speaking, 3 times more energy in this. So if we would use same pressure, same diameter of pipelines, we need 3 of them in parallel to have the same energy transport compared with methane. Yeah? It's worth mentioning, because it's not only saying we have existing infrastructure and we convert maybe today's natural gas pipeline to a hydrogen pipeline. We can do so, but it's only 1/3 of the energy which comes out on the other side. Yeah? And these are simple physics. So this is nothing we really can change. The other thing which is then for sure discussed is how hydrogen can be transported with ships, and the only way, if you really want to transport pure hydrogen on ships, is if you liquefy it. Compressed gas makes no sense at all. And there for a long while, Australia and Japan already have a hydrogen partnership, and Japan already since a long while claims that they want to become a hydrogen country and so on. But they don't have own sources, and what they are looking for at the moment is hydrogen which comes from Australia. Yeah? Australia then uses lignite coal to produce electricity, uses this lignite electricity to produce hydrogen, and then transport the hydrogen to Japan. You don't want to calculate the CO2 emissions per hydrogen, yeah? But this is the other question, other story. But what is worse to understand where we are with the technology, yeah? Because worldwide there's one ship which can transport liquefied hydrogen, yeah? And this is this one here. Yeah? So this is a Japanese-built hydrogen ship which is used then on the route from Australia to Japan. But it is worse to see where we are with the technology. Yeah? So this is a ship with 160 meter length, can transport about 75 to 85 tons of hydrogen, which is about 2.5 to 3 gigawatt hours of energy. If we look what is state of the art in LNG, yeah, so liquefied natural gas. Yeah, this is the QMax class here, and this is a ship with 345 meters of length, has a capacity of 260,000 cubic meters of gas, and transports about 1.6 terawatt hours of energy. Yeah, so this is about 500 times more than the ship. Yeah. So when people talking today about hydrogen economy and that there's very soon hydrogen will be traveling all over the world, the estimations at the moment are that there are capacities to build hydrogen ships in sufficient size to be really competitive in the order of two ships until 2030. Yeah? So half a year ago, our Chancellor and our Minister for Energy and Economics went to Canada and talked with them about hydrogen production, which we can import. And they talked then something about in 2025, the first liquefied hydrogen will come to Europe. I don't know which ship they have in mind. Yeah? I can tell you there won't be a ship. Yeah? And it's difficult to build a pipeline from Canada to Europe, yeah? And with this in time. Yeah? So it is really worse sometimes with some very simple assumptions to ask what are the stories which some people try to tell. Yeah? So this is not the case. Yeah? Liquefied hydrogen, beside the fact that there are not even safety standards defined yet for the harbors. Yeah? So no harbor can build terminals at this point in time because the international standards are not there for safety regulations. Everything is there for LNG. Yeah, this is not the point. This is why we can build in Germany in half a year new LNG terminals. This is a well-established technology. The shipyards are there, the ships themselves, and so on. But for hydrogen, we're really, this is what you always should keep in mind. We're at a very early point in this. There is huge amounts of hydrogen which are used already today from conventional sources. More or less everything comes from natural gas. But this is always just locally used. Yeah? There is no international trading in hydrogen yet. Yeah? So this is a totally new class of challenges. Yes, please.
Okay. As you mentioned, the only way to keep the hydrogen in liquid form is to reduce the temperature to around minus 250 degrees centigrade, right?
Yeah.
So how about the cost to keep the hydrogen in liquid form? Is it high? Is it worth to ship to transfer it by ship instead of using the pipeline?
Yeah, I show you some numbers in a minute about cost. Yeah, but from the technical point, first of all, on the ship, you will not cool the hydrogen anymore. Yeah, so you just put insulation around, insulated vessel. For sure, this is not a 100% insulation. So every heat which goes into the hydrogen simply means that the hydrogen will boil off. Yeah, so you continuously lose liquefied hydrogen. In the ships, we think this is not the major problem because we can use this amount of hydrogen to drive the vessels. Yeah? We can put this into the drive trains of the vessels. Yeah? But for example, if you have a car, a passenger car, and BMW has done for many years, 10, 15 years research on this, having liquefied hydrogen in their passenger cars, just for sure for development purposes. but these tanks were empty after about 7 days. Yeah, so after 7 days, the formerly completely filled hydrogen tank was simply empty, because it disappeared. Yeah, so if you have liquefied hydrogen, you have to use it. But in some applications, as I said, it's not for the passenger car, it's really a problem. Yeah? Especially you don't want to have this car in your garage, because then you always have a critical concentration of hydrogen gas in your garage. Yeah? But for the ship, as I said, we don't care too much about it because we need fuel anyway for the ship. Yeah? Or if we talk about trucks, in trucks generally the problem wouldn't be that high as well, because probably you would have a tank in the truck which contains the liquefied hydrogen for a one-day trip. So every morning before you start your trip, you refill. So this truck will not stand around 6 days a week with a filled hydrogen tank. It will use the hydrogen you fill in the morning, during the daytime, or during the coming 24 hours, and therefore the losses are almost neglectable compared with the use of the hydrogen. So this is also what is very important, to make judgments on technologies only if you analyze the different applications very carefully. Liquefied hydrogen for passenger cars, more or less everybody have understood meanwhile, this is not the way to go. For trucks, it is, because there we go every day with a full tank, and so we won't lose too much by the boiling off. So this is what is really important.
Okay, thank you for your answer.
Yeah, you're welcome. So then when we talk about storing hydrogen, this was about transport, storing hydrogen now, we can store it as a compressed gas, as a liquid, maybe cryocompressed, but this is something very special. Or we can bound it to materials. We can use metal hydrides. There are metals which can bound quite a high share of hydrogen. This is very heavy, but at low pressure. We can have it on solids or in liquids. So we have liquid organic hydrogen carriers which can carry hydrogen. And when we talk about hydrogen storage as a backup, as a long-term storage for this electricity system. I mentioned this morning we need hydrogen, or we need gas to supply the grid up to 3 weeks from gas storage systems. And what we can use in Germany for this is our under-the-ground caverns. These are caverns, mainly salt caverns. So it's very easy to build them. This is nothing where any man or woman was ever in the cavern, because you simply drill a hole, depends 300, 600, 1,000 meters deep, depending on where you have the salt domes, and then you let water run. So you use water to spill out the salt, and this runs maybe 2 years, whatever, and afterwards you have a cavern of several 100,000 cubic meters. And we have a lot of them, because this is where we have our natural gas reserves. So in Germany we have here caverns with a capacity of more than 220 terawatt hour of gas storage capacity. And these caverns could be used most likely also for hydrogen. But again, if you have the same pressure, same volume, it's only 1/3 of the energy which you have inside there. Same problem as with the pipelines. But this is the gas storage with pressures in the range of maybe 100 bars. This is the most relevant storage capacity we have here worldwide. There are ongoing projects in many places of the world looking into the suitability of these caverns for hydrogen storage. There are questions also about the tightness. So do we maybe lose due to diffusion hydrogen in the caverns and so on? This is a small research project. There was a very small cavern but not in salt, I guess, here in Germany. But there have been also large-scale projects with hydrogen caverns in other countries. So we are quite sure that this is working, at least in the majority of the salt caverns. And then we can have either the liquefied gas, so as said or as discussed already, or pressurized gas. The question is to what pressure you would like to go. For passenger cars, the state-of-the-art technology is 700 bars pressurized tanks. They have to be built from carbon composite materials. There is no metal which can withstand these high pressures for long times. As I said, it costs lots of energy to produce them, but yeah, at least it's not that bad. Here comes, by the way, another non-linearity in natural gas. So from the simple simple gas law, we know if you compress a gas by a factor of 2, then, or let me say, if you increase the pressure by a factor of 2 in a given volume, you double the amount of gas inside. So this is simple rule which we all have learned in school. Pressure times volume is the amount of moles times the general gas constant times temperature, I guess. So and if this is constant here, if you increase pressure, then you have more mole. If this is constant, depending. But the problem is, hydrogen does not fulfill this all. So if you compress hydrogen from 350 to 700 bars, I think the amount of energy you can store just increased by a factor of 1.4, 1.5 or something like this. So there's an anomaly as well, so it's not very linear. Nevertheless, so there are different ways, and as you can see also from these pictures up there, there's existing infrastructure, so if you need hydrogen for industrial purposes or for research purposes, you can get it. You get it pressurized, you get it liquefied, whatever you want. So this is well-established technology. Now you can also store it in a different way. You can produce, for example, ammonia. Ammonia is quite interesting because ammonia is nothing else than nitrogen plus hydrogen. And nitrogen is available with 78% concentration in ambient air. So this is very easy achievable. And the other thing is ammonia is basic product in many chemical processes, including, as I said, all the fertilizer production. For example, already by the end of 2021, so even before Russia started the war in the Ukraine, the natural gas price, at least in Europe, increased significantly. And all of a sudden, suddenly there was no production of fertilizers anymore. Because the normal way in chemical industry today is to take natural gas, extract the hydrogen from the CH4, and then this hydrogen is used for the ammonia production. And after the natural gas prices increased so much, it was not beneficial anymore for the companies to produce fertilizers, and therefore we got a shortage for a while on fertilizers. Only after a while, the prices for the fertilizers on the world market increased so much that it became interesting to produce them again. But this is why we had for a certain while a problem in agriculture because of the price problem in the energy sector. You remember what I said? Everything is interconnected, so very heavily. But ammonia also have some have advantages and disadvantages. Can be transported very easily in ships. You can extract the nitrogen from the air, but it is also toxic. So there are always ideas of using ammonia as a fuel for trucks, for example. But most people who are really in this topic are not favorable about this because of the toxicity of the ammonia. So probably this is not a too good idea. And by the way, if you put the ammonia directly in the combustion engine, you get lots of nitrogen oxides, which are also pollutants, so not too easy to work with them. Nevertheless, there are projects ongoing in Saudi Arabia, for example. Saudi Arabia is currently setting up a 2 gigawatt renewable energy system with electrolyzers, and they want to export hydrogen to Europe already in a year or two from now, and this will be ammonia. Yeah, so because for ammonia we have ships, we have infrastructure, we have codes of conduct, we have safety regulations, everything is there. Yeah, so this is a very well-established product. But then, once you have the ammonia in Europe, you should use it as ammonia, yeah? But not extracting again the hydrogen. This costs, again, energy, heat, and so on. Yeah, why going an additional step? Because we anyway need a lot of replacement of ammonia, and this is today all linked to natural gas. So if we can import ammonia from external, we can reduce our demand in natural gas, which is perfect. But it will not give you pure hydrogen in the coming years and decades from this easily. In addition, you also could produce methanol, also a possibility, but for methanol you need CO2. Yeah? And if you look, for example, to these sites in Saudi Arabia, where they build these huge PV systems with electrolyzers, this is desert. Yeah? So there is even no biomass which you may burn or something like this to have a CO2 source. So the only way is there to make this direct air capture we have discussed with the negative emissions. Yeah? Taking the CO2 from the atmosphere, but this again costs maybe 20% of the energy. Yeah? Because it's an energetic process. But methanol could be also easily transported and has a huge demand in chemical industry. And we can do renewable energy methane, yeah? So same chemistry as natural gas, could be transported as LNG and so on, but costs even more energy to produce this. But these are ways to transport hydrogen over long distances in ships. Yeah? But as I said, with this, you don't have hydrogen in the country where you bring it. You have either ammonia, methanol, or methane. And as I said, if you have this, use it first. Yeah? Don't extract the hydrogen, because we need these things anyway. And then we have these so-called liquid organic hydrogen carriers. Yeah? So these are organic liquids which can store a relatively high share of hydrogen, and they are made at the end of the day for just as a storage media. Yeah? So the LOHCs are made to take up the hydrogen on the site where it is produced, and then you bring it where you want, where you need it. Again, to extract the hydrogen there costs also energy. Yeah? So this is then the loaded LOHC carrier on the place where you would like to have it. But then if you want to extract the hydrogen, you need something like heat in the range of 280 to 350 degrees C. Otherwise, you cannot extract the hydrogen from the LOHC again. And this is always also interesting. Then people come along and say, oh, there's enough waste heat from other industrial processes which we can use for this extraction. And there was once in a symposia where there was also the chief engineer of one of the largest German chemical plants. And he said, oh, yes, we have lots of waste energy. But our waste energy has a temperature level of 30 degrees C. Everything above is not waste. Yeah? We have procedures and mechanisms and technology to make use of this. You can have a lot of heat at 30 degrees C if you want. Yeah? And even the heat of a conventional power plant is not at 300 degrees C or something like this. Yeah? The cold side is 50, 60, 70 degrees C, not more than this. Yeah? So this means you have to generate from somewhere the heat. Again, this is one of the problems, and we will see in a minute that the LOHC has also other problems. So what we have then done is we modeled the input. We took the hydrogen as given. We modeled the transport cost, and we looked to the different transport options. And the question if we're using then the hydrogen in material or if we want to re-extract the hydrogen at the end of the day. And there is a report on this as well, just in German right now, but an English version will come, and also an internet tool so that you can go for this if you want. Important for sure is to take into account all these efficiencies. Yeah? So efficiency in transport, transport in pipelines is very efficient. The question is always what is necessary to prepare. Yeah? So if you put directly the compressed gas into the pipelines, you have an overall high efficiency. Here you can see the efficiency on the hydrogen. Here you can see the overall efficiency with regard to the electrical energy generated from renewables. This includes then the efficiency of the electrolyzer as well. And we can see transporting gaseous hydrogen in a pipeline. This gives us the highest efficiencies at all. Whereas if we go, for example, here, the Fischer-Tropsch products, this means the oil-like hydrocarbons, liquid hydrocarbons in a ship, then the overall efficiency is only 37% in energy. That's not used in a combustion engine or something like this, because the Fischer-Tropsch process costs quite a bit of energy. The ship transport, again, is not something which really affects the energy balance significantly. And from this, then finally, we can calculate cost. Yeah? So we calculated cost depending on the distance. So here is the transport distance. The countries which are here on the list, this is distance to Germany. Yeah? So just to have an idea. So for example, from North America, 7,000 kilometers is assumed here. From South Africa, somewhat 12,000 kilometers, and so on. And now we can have a look. Yeah? So for example, using a new build, relatively small pipeline. Yeah? This is expensive. New pipelines are expensive. And if it's a relatively small pipeline, then the prices are really high. On the y-axis, you have euro cent per kilowatt hour. Yeah? Maybe I say some words about this. A kilogram of hydrogen contains 33.3 kilowatt hour of energy. So 1 kilogram of hydrogen is equivalent with 33.3 kilowatt hours of energy. A kilogram of hydrogen today produced from natural gas, or let me say not today, but before, or two years ago. Yeah? So when the natural gas prices in Europe were still dominated by normal gas, pipeline gas from Russia, is in the order of $1 per kilogram. This was used to be a price for hydrogen in the past. Not these days, with the increased natural gas prices anymore. Yeah? But this is what we should think about. Yeah? So this means if the transport of hydrogen costs about 3 cents per kilowatt hour, you have to multiply this with 33 kilowatt hours per kilogram, then each 3 cents is €1 or $1 per kilowatt hour, per kilogram of hydrogen on top. Yeah, so this is the line which already doubles just for the transport, not including the production of the hydrogen or something like this, just for the transport and the losses in the transport chains. Yeah? This is doubling this original price. We won't get back to this, yeah? No question. That's why it's not that bad, but it is always worse to keeping this in mind. Yeah? So a small pipeline with just 300 millimeters in diameter is difficult. If you build a larger one, almost a meter in diameter, then the costs are significantly better, yeah, as you can see here. And now it is worth to compare this with other technologies. for example, or better to say, sorry, this was the retrofit here. Yeah, so this was I go back here. So this is a real, this is a retrofitted hydrogen pipeline. Yeah, so not one which is new build, but this could work very well. This is a pipeline for artificial methane. Yeah, so now you can see a significant offset here, because before you can put it into the pipeline, you have to produce the methane from the hydrogen. Yeah, so you have to take some CO2 from the air, you have to do the processes, and with all of this, significant losses come on top, and therefore you start already with a significant offset. Yeah, this for sure takes into account some prices for the hydrogen and for the electricity which have been used for this. If we would liquefy the hydrogen, the cost will be significantly cheaper, yeah, because we have only the losses for the production, but nothing else. And this for sure is then ship transport. And as almost always, when we have ship transport, the gradient in the cost is relatively low. So it almost doesn't matter if the ship goes 5,000 or 10,000 kilometers. Compared with all the other costs, this is not really of major importance. And this becomes even more obvious when we talk about methanol. Methanol, again, has more cost in producing the methanol first, but once you have put it on the ship, it doesn't matter where you go. So every distance is fine. Ammonia, cheaper to produce, same gradient more or less as methanol, very high density, not too much ship capacity, and so on. If we go to Fischer-Tropsch, so if we make oil equivalent products, then due to the relatively low efficiency of this process, we have very high offset cost, but again, the traveling distance is not really of major concern. And then we have the liquid organic hydrogen carriers. Here you can see, even though this is also a ship transport, you see a quite significant dependency on the distance. What is the reason? The reason is the liquid organic hydrogen carriers themselves are quite expensive. And this means if you have to travel around, by the way, back and forth. So these tankers are filled on the way to where they get hydrogen and on the way back, because you have to bring back the empty LOHC. But you're transporting around an expensive good. And the longer the distance is you go, the lower is the number of cycles you have. If you just travel 1 week, let me say, from the source to where you want to have the LOHC, then 1 week one direction, 1 week back. Every 2 weeks you can earn money with this. If you go double distance, maybe it takes 2 weeks. 2 weeks back and forth, it's 4 weeks in total, so you have only half of the income. You sell only half of the hydrogen within a year, and then you have to still, nevertheless, finance all these LOHC. So this means you have to pay the interest rates for this, and this is the reason why the LOHC has a quite significant dependency on the traveling distance here. This is ammonia with hydrogen recovery. So if we want to get the hydrogen back, we get to this curve here. Therefore, you can see this was ammonia without hydrogen recovery. This is ammonia with hydrogen recovery, because we need, again, a process, and we need energy and so on to get it out of this. So, so by this you can analyze these different technologies, and we are not there yet, but we will also publish this as an internet tool in quite a while, or in some months, better to say. And then you can tune parameters as you want, to see how this affect all this. Because maybe you would not agree to the costs we have assumed for the ships or for the pipelines or whatever, and you would be able to analyze this yourself. But there was a working group of about 20 scientists and engineers, including from the industry. They're covering all these different fields. So there was somebody who develops LOHCs. There was somebody working in the ammonia field and so on. So I think these data are quite well checked against the reality. And with the following, and I don't want to discuss them now here in detail, just want to tell you what you can see. Maybe you're interested to look into this a little more detailed. Here you can see the price for fossil-produced hydrogen, and it contains, on the one hand, here the production price, so in black, for two different scenarios, 1.8 euros per kilogram and 3.5 euros per kilogram of hydrogen. And on top, you have the fee for the CO2 trading. So this is the CO2 price, because if you use the natural gas, then you have to pay as well for the CO2 emissions, and this is what brings the orange bars on top. So these are the reference cases. You see two different prices for the fossil fuels themselves and two different assumptions for the CO2 price. And this then gives you euro cent in kilowatt hour energy in the hydrogen here for the conventional, but for Europe, because it's including the European trading of the CO2 emissions. In the United States, for example, there is no CO2 price on top as far as I know, so you have to subtract the orange part. And then you can compare this with the other options which have been analyzed in this study: pipeline, conversion, U1, the liquefied hydrogen, the tanker with the LOHC, and you always have in dark blue the cost for the hydrogen. You have the cost for the conversion, to make to charge the LOHC, for example, and then the transport itself. This is a pink part on top here. And in the small pipeline, you can see there's no conversion. There's only the transport in the pipeline, whereas for the liquefied, here the conversion is a liquefaction here. The bars for the transport themselves are not really of major impact here. And quite similar things can be looked at for ammonia and methanol. As I said, I won't go into these details yet. You can analyze them in the same way I just have described. And then for sure it also makes sense to compare the things with the reality today. So with increased natural gas prices. No, sorry, this is still January 22. So this was before the Ukrainian crisis, but the price in Europe already has increased there significantly. So the question is where we are with these technologies. So ammonia, this is where we say this is ready to go. The ammonia is a chemical feedstock, so we have everything in place. There are only smaller or minor obstacles, hydrogen into pipelines, methanol, or the Fischer-Tropsch products. Generally, everything from the knowledge, technology is there, not implemented necessarily, but it is generally there. And other things like ammonia for the energy use, so to cracking the ammonia again to extract the hydrogen, or the methane thing, or the liquid hydrogen and the LOHC. This is not ready for large-scale industrial use yet. So there is technology available at relatively high technology readiness levels, but this is not ready yet because in many cases it still needs also international agreements on standards and so on. So finally, we can say that there are various options, and it will be interesting to see which of these things will start or which will happen first. But it has also a significant impact then on the question which sectors will get the hydrogen first. For example, I mentioned the Saudi Arabian project is maybe the first one which will ship significant amounts of hydrogen covered in ammonia to Europe, but this means this will go completely to the chemical industry. No trucks, no passenger cars, no gas turbines, nobody will use this ammonia. This goes 100% to the chemical industry first. And by this, we also set lines of technology development at the end of the day. And nevertheless, always keep efficiency in mind. Efficiency costs money, and also the power generating units are not for free. They also, by the way, need raw materials. If you say, I don't care about efficiency, let us build a double number of, or we double the number of wind turbines. This, by the way, means also you need to double the amount of concrete, which is necessary for the fundamentation. You need to double the amount of steel, which is needed for the towers. It's doubling the amount of copper you need in the generators, and so on, and so on, and so on. And this all has to come from somewhere. And once again, as I said, mining generally is a dirty business. Not everywhere and for all of the different materials in different levels, but nevertheless, it is always a challenge for those who live around these mines in any case. And the transport, according to what we have calculated, you can see 4 to 8 euro cent is easily what you have to add. So this is a 2 euro per kilogram. Just to keep this in mind, as in the past we had these very nice low prices of euro or dollar per kilogram of hydrogen. In the future we just will have for the transport another 2 euros or dollars on top. So things will not be that cheap anymore in the future. Again, this is a clear statement for high efficiencies.